Hello. Yeah, hi. I'm Michael Günther from the database group of the Technical University of Dresden, and I present FacetE, an automatically constructed large evaluation data set for word embedding models, which are very widely used in natural language processing system. And I will also explain the extraction process. In NLP systems, data is usually processed by taking some pieces of text from a large storage of textual data, and then it's transformed in some numerical representation by some language modeling technique. And here, word embedding models are very widely used across many different NLP tasks, and these models utilize large text corpora like all English Wikipedia articles and use them to do training on a dummy task, like taking some sequences of words out of these text, masking some words, and try to predict these masked words. As a byproduct, these neural networks learn to transform words into some vectors of weights, and the trick is then to export the model weights as pre-trained language models, which can then be used to model almost any textual representation in numerical vectors, which can then be used as input for some classification and regression tasks or for some similarity search tasks. Yeah, word embedding models find application obviously in many machine learning systems, which can utilize the implicitly encoded knowledge from these large text corpora. And moreover, machine learning models can better generalize by using those vectors as input than by using a syntactic representation of these words, because these vectors capture the semantic similarities of the text values. In the database community, word embedding are also used. Recently, some text similarity queries are implemented based on word embedding models and algorithms for data exploration and data integration tasks. And finally, also information retrieval system make use of word embedding models for semantic search features to implement algorithms for query expansion and for multilingual search features, to just give some examples here. For all those applications, the choice of the right pre-trained word embedding model is very crucial for the performance of these algorithms. And so we come now to the evaluation. Word embedding models are often evaluated by some arithmetic properties. And here, for example, word similarity can be quantified by calculating the cosine similarity of word vectors. And here in this schematic image, for example, we could see that the most similar to king, according to the cosine similarity, are prince, queen, and man. Word embeddings also capture the semantic similarity between relations of words by the cosine similarity of difference vectors of words. This can be utilized to solve analogy questions like what is to king like woman to man, and therefore the arithmetic operations like this 3 cos at operation we can see here can be used, and in this example the answer would be queen. So now we want to look at common evaluation data sets and their limitations. So the NLP community constructed a lot of data sets with some word pairs and a human judgment of their similarity. Two common examples are the WS353 data set, which contains a few hundred word pairs and quantify for them semantic relatedness. SimLex is also a common data set used here. In contrast to the other data set, it focused more on semantic similarity. To construct such data sets, however, a large amount of human labeling effort is necessary to produce high quality data sets. Also common are data sets with analogy queries. So here Google Analogy and MSR are very popular. They contain a few hundred relations from which a few thousand analogy queries can be constructed. And yeah, this data sets can also be constructed in a more automatic fashion. Then if we look at papers which use such data sets, we often see something like this. So in case of the similarity data sets, often for the data set, the correlation with the similarity calculated by a word embedding model is reported. And for the analogy data set, the amount of correctly solved analogies with a specific analogy method is reported. As we can see here, for example, in the results of the paper which introduced popular word embedding model, the Clovey model. This has some limitations. So on one hand, we can see that the data sets we see here at least have a very small number of relations. We have for each data set just a single number of quality reported, which does not give us much information about which words have actually good representation and which do not. And all the terms which are usually stored in these data sets are from a very generic domain, and we cannot obtain a domain-specific evaluation with these data sets. So our design goals were therefore to construct an analogy data set with a larger number of relations and a flexible structure that allows a tester to extract some pieces from this data set to construct its own evaluation data set, which then fits to a specific application task, and also define some categories for domain-specific evaluation. And we achieved it by using millions of web tables from which we want to extract relations, organize them in a facet classification system, which allows us, which gives the desired flexibility, and we want also defined categories for the domains. Yeah. Web tables are our data source because they contain a large amount of public available knowledge and knowledge which is general enough to be expected to be represented in pre-trained word embedding models, and they contain a lot of redundancy in the data. This is also good for us because we can use them to determine static facts, which are preferred in contrast to conditional or temporary facts, like if we have soccer games, which is the visiting team for a given home playing team, this always depends on this specific soccer game to a specific point in time. We organize the extracted data in facets. That means we have an object set like soccer players, from which each term is assigned to exactly one value in a value set, like these teams here. And it is stored as a tuple of this object and value set in our data set. With these facets, then the tester can, as I said, can extract specific object sets or specific facets which fit to the task to construct its own evaluation set, and that gives a bit, the facet structure gives a bit more flexibility than if we would choose a hierarchical organization of relations. So now we come to the extraction pipeline. The extraction pipeline takes tables from the DWTC web table corpus, which is a corpus about 125 million web tables, and it extracts from it in roughly 4 steps our FacetE dataset. In the first step, pre-filtering is done. Here, for example, we exclude non-textual data and like the date column, which cannot be evaluated efficiently by word embedding models, and we also exclude infrequent columns like this nickname column, which because it only appears very infrequently together with the other columns in the table. And after that, we built all combinations of tuples from the remaining data, and this is the basis of our facets. In the next step, we want to determine which are static facts by calculating so-called soft functional dependencies. First here, we determine the most frequent relation pairs like Arsenal, England. And then we also determine for the object, which is in this case Arsenal, or other tuples like Arsenal, United Kingdom, which we call contradictions. And then we calculate the soft functional dependency value, which determines the amount of non-contradictionary tuples, which is 2/3 in the case of Arsenal, England. And then we only retain word pairs which occur frequently enough and which have a high enough SFD score. In the third step, we want to exclude two generic facets by applying some blacklists on the headers of the object and the value set of our facets. Something like name description would not make up a good facet for domain-specific evaluation, for example. And then we also apply word embedding pooling. This means we take for each facet some samples and evaluate them on a set of very common large word embedding models. And only if at least one word embedding model has a significant accuracy on this data set, then the facet is retained, otherwise it's thrown away. And finally, we assigned the facets into 8 broader categories. And herefore, we take the terms of object and value set as well as the word pairs itself, put them into a word embedding model to then calculate similarity scores according to some keywords we define for each category, and then select the category with the highest score, similarity score, which is an aggregated similarity score of the similarity scores calculated before. And in this case, it would be sports. Now we want to show you a demonstration on an exemplary evaluation we did. Here we have 4 pre-trained word embedding models and 4 categories of our FacetE dataset. And then for each facet in each category, we use the word embedding models to determine the value for each object term with the 3-cos-add analogy method, and then calculate the amount of correctly assigned values for each facet. The distribution is shown in these wireline plots, and we also calculate the average across all facets in one category for each word embedding model. Since some terms cannot be represented by all word embedding model into a vector representation, we also report the coverage values here. And as one can see, there is no best model which achieves the best performance in all categories, and there's a high coverage in general. Then we also want to demonstrate an evaluation on a single object set. Therefore, we take the same word embedding models and select all facets out of our data set with the object set of city terms. And then we also use the 3-cos-add method and the word embedding models to determine for each object term, for each city, specific values for each facet. And now we calculate the amount of correctly assigned values per city term. So not per facet. And here on the right, the distribution is shown for that. And then we also calculate the average across all objects. And what we can see here in comparison with the geographic evaluation is that word2vec has performed best on the geographic domain in general, but the Globi dataset has performed better on the city terms. So now we come to the conclusion. In this talk, I represented extraction pipeline to extract a word embedding evaluation data set from a large web table corpus. You can imagine that we can also reuse this pipeline for other table corpora, like if we have some set of CSV files in a company from which we want to construct an evaluation data set. As a structure, we should choose to organize it into facets, which allows a flexible construction of a specific evaluation data set, and it's enabled us to do an evaluation on different capillarities. So we can evaluate a single facet, we can evaluate certain objects or a specific domain. And our evaluation on common word embedding models shows that there are large differences in the accuracy values for different word embedding models on different domains. And there's no best model for all cases. So this also motivates this construction of the dataset. We published the dataset on the data science platform Kaggle. And yeah, with this, I want to thank you for the attention and go over to questions.
Thanks for the talk. We have some time for questions. Any questions or comments?
Hi, yes. Thanks for the talk. This sounds like a lot of work. How much manual work did you need to put into this? How often did you sample whether the data that you collected actually made sense and that kind of stuff?
Yes, so the real manual work was to define these keywords for the categories and also these blacklists. Because we don't have a good automatic way to determine which are such two generic facets. Otherwise, most of it is run automatically. And I think the data quality is quite okay, especially for evaluating such word embedding models. However, maybe it does not has, and it also does not need this quality which you may expect from a knowledge base, for example. So one thing which is a bit problematic, for example, would be that the relations are not so coherent, but I think this is not so much a problem here for this purpose.